Welcome to this coding problem walkthrough. In this session, we will tackle LeetCode problem number 711, titled Number of Distinct Islands 2. This problem challenges us to identify unique island shapes in a grid, accounting for transformations like rotations and reflections. Let's dive in and explore how to solve it step by step. In this problem, we are tasked with identifying the number of distinct islands in a 2D grid. The grid is represented as an MXN binary matrix, where each cell is either 0 for water or 1 for land. An island is defined as a group of connected 1s, where connectivity is limited to horizontal and vertical directions. All four edges of the grid are surrounded by water, so islands are always enclosed. Now, an island is considered distinct only if its shape cannot be transformed into another island's shape by applying any combination of rotations 90, 180, or 270 degrees, or reflections, such as flipping horizontally, vertically, or diagonally. Our objective here is to determine how many unique island shapes exist in the given grid, accounting for these transformations. The input to the problem is the 2D binary matrix grid, and the output is an integer representing the count of distinct islands. Let's look at an example to understand this better. Imagine the grid is as follows: 1, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0. Here, the grid contains two islands. The first island is in the top left corner, made up of 3 cells with coordinates 0, 0, 0, 1, 1, 0. The second island is in the bottom right corner, consisting of 4 cells with coordinates 2, 3, 2, 4, 3, 3. These two islands initially appear to be different, but we need to account for transformations to determine if they are distinct. After applying rotations and reflections, we find that the second island's shape can be transformed to match the shape of the first island. This means that, although there are two islands in the grid, they are not distinct because their shapes can be made identical through transformations. As a result, the output for this example is 1, representing a single distinct island. Now, consider another grid, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0. This grid contains two islands. In the second example, the first island spans the entire left side of the grid. It includes cells with coordinates 0, 0, 0, 1, 0, 2, 1, 0, 2, 0, 2, 1, 2, 2. The second island is smaller and isolated at the bottom right corner. Importantly, these two islands have distinct shapes that cannot be transformed to match each other through rotations or reflections. Therefore, the output for this grid is 2, indicating two distinct islands. Let's now review the constraints and edge cases for this problem. The grid dimensions are constrained such that m and n can range from 1 to 50, and the total number of cells, m*n, will not exceed 2500. Each cell in the grid is guaranteed to be either 0 or 1. Some important edge cases to consider include when the grid contains only water, resulting in an output of 0, or when there's exactly one island, which would always give an output of 1 regardless of the island's shape. If there are multiple identical islands, their transformations must be accounted for to avoid double counting. On the other hand, if all islands have unique shapes, the output will simply be the total number of islands. Lastly, the algorithm must be efficient enough to handle large grids near the maximum constraint of 50x50. To begin, let's consider the brute force approach. The intuition here is straightforward: we identify all islands in the grid, store their shapes exactly as they appear, and then compare every pair of islands to determine whether they are distinct. However, there's a major challenge with this method. Islands can appear in different orientations, such as rotations and reflections, and this approach doesn't account for those variations. To handle this, we would need to normalize each island by generating all possible transformations, rotating and reflecting the island in every way, before making comparisons. Unfortunately, this normalization process is computationally expensive, especially on larger grids. The time complexity grows as k*n squared, where k is the number of islands, and n*2 accounts for the cost of normalizing each island. Similarly, the space complexity is also k*n squared, because we need to store all these shapes and their transformations. While this method is simple to implement, the computational inefficiency and redundancy make it infeasible for large-scale problems. Now, let's shift to an optimized approach that leverages normalization combined with hashing. The key insight here is that two islands can be considered the same if one is simply a rotated or reflected version of the other. To efficiently handle this, we normalize the shapes of islands so that they can be compared consistently. This involves several steps. First, we extract the coordinates of each island relative to its top left corner. Next, we generate all 8 possible transformations of the island, 4 rotations and their reflections. Among these, we select the lexicographically smallest transformation as the island's canonical form. This ensures that each unique island is represented in a standardized way. Once we have the canonical forms, we use a hash set to store them and count the distinct islands. The process involves performing DFS or BFS to identify all islands in the grid, translating each island to the origin, generating and selecting the canonical form, and finally storing the form in the hash set to avoid duplicates. By the end, the size of the hash set gives us the number of distinct islands. This optimized approach is particularly effective because it avoids redundant comparisons by focusing entirely on canonical forms. By utilizing hashing, we efficiently handle duplicates, even when accounting for rotational and reflective equivalences. The time complexity for this approach is O(m*n*k), where m and n are the grid dimensions, and k represents the average size of an island for normalization. The space complexity is O(k*t), where t is the number of unique canonical forms stored. While this method is slightly more complex to implement than brute force, it is significantly faster and scales much better for larger grids. One of the key observations here is that the real breakthrough comes from understanding that all rotational and reflective variations can be condensed into a single canonical form. This eliminates the need for exhaustive pairwise comparisons. Alternative methods, such as directly comparing shapes without normalization, fail to account for transformations or become computationally prohibitive. By balancing clarity and efficiency, this approach provides an ideal solution to the problem of counting distinct islands. The problem we're solving involves identifying distinct islands in a 2D grid where ones represent land and zeros represent water. An island is defined as a group of connected ones, and connectivity is limited to vertical or horizontal adjacency. The challenge lies in determining the number of unique island shapes, where uniqueness accounts for variations due to rotations and reflections. To tackle this, the algorithm starts by parsing the grid and initializing a set called unique_shapes to store normalized versions of island shapes. A depth-first search helper function, or DFS, is defined to explore each island and capture its shape. The grid is then traversed cell by cell, and when a land cell is encountered, the DFS function is triggered to map out the entire shape of the island starting from that cell. The depth-first search, or DFS, is the core of this algorithm. The DFS function is designed to explore the entire island starting from a given cell. It begins by marking the current cell as visited by setting its value in the grid to 0. During exploration, each movement direction up, down, left, or right is recorded in a list called path. This ensures that the traversal is encoded uniquely. The function continues recursively for all valid neighboring cells. To handle backtracking, a special movement marker, B, is added to the path whenever the DFS returns to a previous state. Once the DFS is complete, the path represents the island's traversal signature. However, since islands can appear in different rotations or reflections, the path is normalized by generating all 8 possible transformations of the shape and selecting the smallest one lexicographically. This normalized path is then added to the unique_shape set. Finally, the total number of unique islands is determined by the size of this set, which is returned as the result. A few key insights make this algorithm effective. First, using directional encoding, such as U4 up and D4 down, ensures that each island's shape is uniquely represented. This encoding is relative to the starting point of the traversal, which eliminates dependency on the island's specific position in the grid. Second, normalization through transformations handles the challenge of identifying identical shapes in different orientations. By generating all rotations and reflections and selecting the smallest transformation, the algorithm ensures that each shape is represented consistently, regardless of its appearance in the grid. Third, the inclusion of backtracking markers, like B, allows the algorithm to differentiate between paths that might otherwise appear identical in length and directionality. Lastly, using a set to store these normalized shapes ensures that the algorithm efficiently tracks uniqueness while avoiding redundant computations. The algorithm relies on three primary data structures. The first is the grid itself, which is represented as a list of lists. This grid not only holds the input data but is also updated during the DFS to mark cells as visited, preventing duplicate exploration. The second key data structure is the unique underscore shapes set. This set is used to store the normalized traversal paths of islands, ensuring efficient lookup and storage of distinct shapes. Finally, the path list is crucial during DFS. It records the sequence of movements as the algorithm traverses each island, capturing its shape in a way that can later be normalized. Together, these data structures allow the algorithm to process the grid systematically and identify distinct islands with minimal overhead. Several edge cases must be considered to ensure the robustness of the solution. First, when the grid contains only water represented entirely by zeros, the algorithm correctly returns 0, as there are no islands to count. Second, the algorithm handles single-cell islands by treating isolated ones as unique shapes. Third, the normalization process guarantees that identical shapes in different orientations, such as rotations or reflections, are recognized as the same island. This is critical for maintaining consistency in the count of unique islands. Lastly, the algorithm is optimized to handle large grids, up to the constraint of 10 to the power of 4 cells. By normalizing shapes and avoiding redundant computations, it remains efficient even for grids at the upper size limit, ensuring scalability. Here, we define the main function number distinct islands 2, which takes a grid as input. To start, we use a helper function called DFS to perform a depth-first search. The goal of DFS is to explore all the connected cells of an island, marking them as visited by setting their value in the grid to 0, and recording their relative positions in the shape list. The relative positions are calculated based on the starting coordinates of the island, represented by base_x and base_y. This way, the shape of the island is always described relative to its top left corner, regardless of its position in the grid. Inside the DFS function, we iterate over all possible directions right, down, left, and up, checking if the neighboring cell is within bounds and part of the island. If so, we recursively call DFS on that cell to continue exploring. Next, we define another helper function, normalize, which ensures that island shapes are stored in a consistent format. Since islands can appear rotated or reflected, we generate all possible transformations of the shape. This includes rotations, by swapping x and y coordinates, and reflections, by flipping the signs of the coordinates. Each transformation is sorted to maintain consistency, and finally, we standardize each transformed shape by shifting its coordinates so that the smallest x and y values are 0. This guarantees that all identical shapes, regardless of orientation, are represented in the same way. The normalize function then returns the lexicographically smallest transformation, which serves as the canonical representation of the island's shape. Now, we proceed to the main logic of the program. First, we initialize an empty set called unique_islands to store the normalized shapes of all distinct islands. The directions list, which defines the 4 possible movement directions, is also declared here. We then iterate over every cell in the grid using nested loops. If we encounter a cell with a value of 1, indicating the start of a new island, we initialize an empty shape list and store the current cell's coordinates as the base point, base_x, and base_y. We then call the DFS function to explore the entire island and extract its relative shape. Once the shape list is complete, we pass it to the normalize function to get its canonical representation. This normalized shape is added to the unique_islands set, ensuring that only distinct shapes are stored. Finally, the program returns the size of the unique_islands set, which represents the total number of distinct islands in the grid, accounting for all rotations and reflections. Here, we begin implementing the solution for the number of distinct islands 2 problem in Java. The method number distinct islands 2 takes a 2D grid as input, where each cell is either land, represented by 1, or water, represented by 0. We start by determining the number of rows and columns in the grid and initializing a hash set called unique islands to store the distinct island shapes. We also define an array directions to represent the possible movements right, down, left, and up. The nested for loop iterates through every cell in the grid. When we encounter a land cell, we initialize a list to store the shape of the island and perform a depth-first search using the DFS helper method. This method explores all connected land cells, marks them as visited by setting their value to 0, and records their relative positions in the shape list. Once the DFS is complete, we normalize the shape of the island using the normalize method, which converts it into a canonical form. This ensures that identical islands, even if rotated or reflected, are treated as the same. The normalized shape is then added to the unique islands set. After processing the entire grid, the size of the unique islands set, representing the number of distinct islands, is returned. In the DFS method, we mark the current cell as visited by setting its value to 0 and record its position relative to the starting point of the island in the shape list. Then, for each of the 4 possible directions in the directions array, we calculate the coordinates of the neighboring cell. If the neighbor is within bounds and is land, we recursively call the DFS method to continue exploring the island. Next, we move on to the normalize method, which is used to generate a canonical representation of an island's shape. This method considers all possible transformations of the shape, including rotations and reflections. For each transformation, we generate 2 versions of the shape, one based on the original coordinates and another based on swapped coordinates. These transformations are stored in a list called transformations. By normalizing the shapes, we ensure that 2 islands that are identical in structure but differ due to rotation or reflection will yield the same canonical form. Finally, the smallest string representation among all transformations is returned as the normalized shape. The serialize method is a utility function used to convert the shape of an island into a unique string representation. First, the shape is sorted based on the x coordinates, and in the case of ties, by y coordinates. This ensures that the shape's points are ordered consistently. Then, we calculate the offsets for the x and y coordinates using the first point in the sorted list. These offsets are subtracted from each point to align the shape to a common origin. A string builder is used to construct the serialized string by appending the relative coordinates of each point, separated by commas and semicolons. This string representation allows us to compare different shapes efficiently. By combining this serialization process with the normalization logic, we can accurately identify and count distinct islands, regardless of their orientation or reflection. Let's start with a simple grid that has rotational symmetry. The input grid here is a 2x2 matrix where 3 cells form an L-shape island. To solve the problem, we first initialize a set called unique_islands to keep track of distinct island shapes. We also define the possible movement directions, right, down, left, and up. Now, we focus on finding the first island. The traversal begins at cell 0, 0, which is part of the island since its value is 1. We initiate a depth-first search, DFS, from this cell, setting its coordinates as the base reference point and initializing an empty list to store the island's shape. During the DFS traversal, we first visit 0, 0, at its relative position to the shape, and mark the cell as visited by setting it to 0. Then, we move to the adjacent cell, 0, 1, at its relative position, and mark it as visited. Next, we move to 1, 0, do the same, and mark it as visited. At this point, there are no more valid moves, and the DFS completes, capturing the island's raw shape as 0, 0, 0, 1, 1, 0. Once we have the raw shape of the island, we proceed to normalize it. Normalization involves generating all possible rotations and reflections of the shape. For this example, we calculate transformations like 0, 0, 0, 1, 1, 0, 0, 0, minus 1, 0, 0, minus 1, and others. Each transformation is then normalized by aligning it to the origin, ensuring the minimum coordinate starts at 0, 0. Among all normalized transformations, we select the lexicographically smallest one, which in this case is 0, 0, 0, 1, 1, 0. This normalized shape is then added to the unique_islands set. Finally, since there are no other islands in this grid, the size of the unique_islands set is 1, and we return this as the result. Now, considering a new example grid, we have a 3x3 matrix with 2 distinct islands. We repeat the same process, starting with the first island at 0, 0. Using DFS, we discover its shape as 0, 0, 0, 1, 1, 0, normalize it to 0, 0, 0, 1, 1, 0, and add it to the set. After processing the first island, we move on to the second island located at 2, 2. Starting the DFS from this cell, we find that the island consists of only one cell, represented as 0, 0. Normalizing this shape doesn't change it since it's already anchored at the origin. We add this second shape to the unique underscore island set. At this point, the set contains two distinct shapes, 0, 0, 0, 1, 1, 0, and 0, 0. As a result, the size of the unique underscore island set is 2, and we return this value. Now, let's consider a scenario where the islands have rotational equivalence. In this 2x2 grid, the island is shaped like a mirrored L, starting from cell 0, 0. Using DFS, we identify its raw shape as 0, 0, 1, 0, 1, 1. To handle the rotational equivalence, we again generate all possible transformations, including rotations and reflections, for the discovered shape. After normalizing each transformation, we find that the lexicographically smallest normalized shape is 0, 0, 0, 1, 1, 0. This shape is then added to the unique underscore islands set. Since all islands in this example are rotationally equivalent, the set contains only one unique shape. Therefore, the size of the unique underscore islands set is 1, and that is the result we return for this grid. Here, we start by analyzing the time complexity of our solution. First, we need to traverse the entire grid to locate all the islands. This requires iterating through every cell in the grid, which takes m*n time, where m is the number of rows and n is the number of columns. For each cell that is part of an island, we perform a depth-first search, or DFS, to explore the entire structure of that island. The DFS process ensures we visit every cell of the island exactly once. Since each cell in the grid can belong to at most one island, the total time spent in DFS across all islands is also m*n. These two steps together make up the base cost of traversing and exploring the grid. Next, we have the normalization step, which processes the shape of each island to ensure uniqueness under rotations and reflections. For each island, the normalize function generates 8 transformations, 4 rotations and 4 reflections. Sorting the shape of the island during this process takes k*log, k time, where k represents the number of cells in the island. Additionally, adjusting the coordinates for these transformations takes k time. When we account for all islands in the grid, the normalization step has a worst-case cost of m*n*log, k, where k is the average size of an island. Since k can grow up to m*n in the worst case, this simplifies to m*n*log m*n. Finally, adding these normalized shapes to the unique underscore islands set involves inserting tuples. While insertion and lookup in a set are generally 1, in the worst case, inserting a tuple proportional to the size of an island costs k. Across all islands, this step contributes m*n to the overall time complexity. Altogether, the normalization process dominates the runtime, giving the solution a worst-case time complexity of m*n*log m*n. Now, let's examine the space complexity of the solution. The DFS traversal is recursive, so it uses stack space proportional to the depth of the recursion. In the worst case, this depth could be as large as the size of the largest island, which is m*n. For storing the shapes of the islands, we allocate k space per island, where k is the size of the island. Across all islands, this requires m*n space. The normalization step generates 8 transformations for each island, with each transformation needing k space. This results in a total space requirement of m*n for transformations. Finally, the unique underscore island set stores the normalized shapes as tuples, with each tuple requiring k space. In the worst case, the total space for the set is also m*n. Combining all of these, the overall space complexity of the solution remains m*n. The overall space complexity is dominated by the storage of island shapes and transformations, resulting in a worst-case complexity of m*n. Comparing this to a brute force approach, the naive method would involve comparing every pair of islands, which has a time complexity of I²*k, where I is the number of islands and k is their average size. With I potentially being m*n, the brute force approach could reach a complexity of m times n (*k). In contrast, our solution avoids this inefficiency by normalizing each island's shape and checking uniqueness using a set, greatly improving the runtime. Regarding space usage, both the brute force and the proposed solution require O(m*n) to store island shapes. However, the brute force method might incur additional overhead for pairwise comparisons, whereas the proposed solution minimizes this by leveraging normalization and hash set operations. Finally, we can break down the best, worst, and average case scenarios. In the best case, when the grid contains no islands, the solution only needs to traverse the grid, resulting in a time complexity of O(m*n) and a space complexity of O(m*n). For the worst case, where the entire grid forms one large island, the normalization step becomes the dominant factor. This yields a time complexity of O(m*n)log(m*n) and a space complexity of O(m*n). In the average case, when the grid contains multiple smaller islands, the time complexity remains O(m*n)log(m*n) due to normalization. This step scales with the total number of cells in all islands, making it the most significant contributor across most scenarios. When solving this problem, there are several common mistakes to watch out for. First, not accounting for rotations and reflections can lead to incorrect results. Two islands may appear different but are actually the same when flipped or rotated. To handle this, you need to normalize the island shapes, often by converting them into a canonical form. Second, modifying the grid directly during traversal, such as marking visited nodes, can cause unintended side effects. For example, you might accidentally skip valid islands or revisit cells if safeguards are not properly implemented. Using a separate visited structure can help prevent this. Third, inefficient shape comparison is another pitfall. Storing raw coordinates for island shapes and comparing them directly is computationally expensive. Instead, consider encoding shapes into unique strings or hashes, which will save both time and space. Finally, don't overlook edge cases. Grids with no islands, all land, or even small grids like 1x1 or 1xn, require special handling. Ensuring your solution is robust across different grid configurations is essential for correctness. Now, let's discuss a few more important points. Using DFS without managing recursion depth can be problematic, especially for large grids, as it may exceed Python's recursion limit. To address this, you can use an iterative approach with a stack or carefully adjust the recursion limit if needed. From an interview perspective, normalizing the island shapes is often the crux of this problem. Your ability to represent shapes uniquely, regardless of their orientation, is key to solving it effectively. Recognizing patterns is also important. This problem shares similarities with other grid-based problems that use floodfill techniques, like DFS and BFS. It's a good idea to practice these techniques to build confidence. When optimizing your solution, focus on minimizing both time and space complexity. For instance, hashing normalized shapes is far more efficient than storing and comparing raw coordinates. Lastly, when explaining your solution, be sure to clearly articulate how you handle edge cases and why your normalization ensures correctness. This demonstrates both your understanding and attention to detail. There are also several related problems that can help deepen your understanding of grid-based challenges. For example, in LeetCode 200, number of islands, the focus is on counting disconnected islands using DFS or BFS. LeetCode 1254 introduces a variation where you identify islands that are fully surrounded by water, called closed islands. LeetCode 1020, number of enclaves, requires careful handling of land connected to the grid's boundaries, which adds an extra layer of complexity. Finally, LeetCode 1905, count sub-islands, tests your ability to compare sub-islands between two grids to determine which ones are entirely contained. Each of these problems builds on similar concepts, so practicing them will improve your problem-solving skills and help you recognize patterns that are common in grid-based questions. Finally, let's explore some alternative approaches to solving this problem. One option is using DFS with normalization. Here, you traverse each island and record its relative shape. To ensure consistent comparison, you normalize the shape by sorting or rotating it into a canonical form. This method is intuitive but may require extra post-processing to handle normalization effectively. Another approach is BFS with hashing. In this method, you use BFS to traverse the grid, encode the island shapes directly into a hashable format, and store them in a set for comparison. While this avoids recursion issues and is efficient, you must carefully handle potential hash collisions. Lastly, the union find or disjoint set approach can be used to group connected components and identify unique island shapes. This method is efficient for certain types of grid problems, but it tends to be less intuitive when it comes to encoding and comparing shapes. Each of these methods has its trade-offs, so the best choice will depend on the specific constraints and requirements of the problem. Thank you for following along with this problem walkthrough. In this session, we explored how to identify distinct island shapes in a grid, and we discussed approaches like brute force and optimized methods. Remember to practice similar grid-based problems to strengthen your skills, and stay tuned for more content to help you ace your coding interviews. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!